I would like to give you a warm welcome to this video. My name is J.Renner, and I would like to present the paper about randomized decoding of Gabidulin codes beyond the unique decoding ratings. So let me switch to my slides such that we can start with the presentation. What I would like to emphasize at the beginning is that the work that I'm presenting here is joint work with T.Jerkovits and H.Bartz from the German Aerospace Center, Sven S.Puchinger from the Technical University of Denmark, P.Loidreau, who is affiliated with the University of Rennes, and Antonia A.Wachter-Zeh, who is also from the Technical University of Munich. I will claim that most code-based crypto systems are based on the hardness of decoding an error of small Hamming or small rank weight in a random code. However, in my opinion, there are also different or other decoding problems which might be suitable. And one of them is the following, namely decoding an error of large rank weight in a Gabidulin code. This problem is conjectured to be hard and also partly proven. So what is the difference to the previously mentioned problem? Namely, instead of a random code, we have here a Gabidulin code, and we assume that the structure of this Gabidulin code is also known. Furthermore, instead of a small weight of the error, we have a large weight of the error. And what I mean by large will be formally defined later. What was shown is that systems based on this problem have the potential to have very attractive small key and ciphertext sizes. And what we do in our paper is that we propose a new algorithm to solve this problem. And this is very important to assess the security of the mentioned systems. Okay, I think that most people are more familiar with the Hamming metric than the rank metric. So the idea was, well, my idea was to give you the idea of our algorithm in the Hamming metric and then show how this translates to the rank metric. Just to avoid confusion, we don't cover what I'm showing in the Hamming metric in our paper. So we're just treating the rank metric in our paper. But still, I think this helps you to getting started with our paper. So the Hamming weight of a vector is defined as follows. Assume we have a vector A of length n over the extension field FQM. Then we say its Hamming weight is equal to the number of non-zero positions of the vector. A further definition that we need is the definition of Reed-Solomon codes. This code class is very good in correcting errors in the Hamming metric, and they can be defined by their generator matrix. So assume we have elements alpha 1 up to alpha n of the extension field FQM, which are non-zero and distinct, and also nu1 up to nu-n, also from the extension field, and also non-zero elements. Then the code, or the Reed-Solomon code, can be defined by this generator matrix, where we have a matrix which has in each row the elements alpha 1 up to alpha n, and we power them from 0 up to k minus 1. And then we multiply this matrix by a diagonal matrix, where we have on the diagonal nu1 up to nu-n. Then with these two definitions, we can already look at problem 1. Just to emphasize it once more, you cannot find this problem in our paper, but I introduce it to get you familiar with our idea. And problem 1 is called search Reed-Solomon codes. It has an instance, a Reed-Solomon code specified by this generator matrix. We get a vector R, which is the code word or a code word of this Reed-Solomon code plus an error. And now the important thing comes, namely that the Hamming weight of this error is larger than n minus k half and smaller than n minus k. The objective of this problem is that one should find a vector m hat such that the weight of R minus m hat times the generator matrix is smaller than the Hamming, or smaller or equal than the Hamming weight of this vector E. I write here m hat because this m hat does not necessarily have to be the same as this m here, but any m which satisfies this is a solution to the problem. Okay, now let's look at the idea of our algorithm in the Hamming metric. what we know is that there are efficient algorithms for these Reed-Solomon codes, which can correct errors of Hamming weight smaller or equal to n minus k half very efficiently. And what I mean with can decode, they are capable of correcting all these errors, not only with the high probability, but all of them. Now, if you look at the instance of the problem, you can see that the Hamming weight of this vector is larger than this quantity, which means we cannot apply these algorithms directly. However, we can do something else to decode it. Namely, what we do, or what the idea of our algorithm is, that we ignore delta positions in this vector R and delta columns of the generator matrix. If you denote this by coding terms, you would say that you insert delta erasures. What you obtain is that the code length now is decreased to n prime, which is equal to n minus delta, obviously. Then the dimension of the Reed-Solomon code stays the same, so k prime is still equal to k. And on this remaining positions, we now have still an error, but this error has now a weight of wh prime. And this wh prime is equal to wh minus epsilon. So basically epsilon is a value that indicates the number of erroneous positions that we ignored. And now if we say that this new error weight on the remaining positions is smaller than this quantity, then we can apply these efficient algorithms that I just mentioned to correct the error. Okay, and we can rewrite these conditions in the following way, saying that if the number of erroneous positions that we ignored is larger than this quantity, our strategy works. Now, what is the problem? The problem is that we don't have any information about the error, so we don't know the error positions or which positions we should ignore. So what we do in our algorithm is that we guess these positions. Let's look at an example, then I think it becomes more clear. So assume that at the beginning our code length is equal to 7, the dimension of the code is equal to 3, then the Reed-Solomon code has an error correction capability of 2. Furthermore, we assume that the Hamming weight is equal to 3, so this means that the efficient algorithms that we know cannot correct it, and we want to ignore 2 positions. Further, we assume that this vector R is a code word plus an error, and we see that the second, third, and sixth position is erroneous. Then according to what I just told you, we now guess 2 positions and assume in the first case that we guess or we ignore position 2 and 4. Then the vector that we obtain, so this R prime, has errors on this and this position. So the Hamming weight of the error on the remaining positions is equal to 2. The new code length is equal to 5. The dimension stays at 3, which means that we are able to correct 1 error. However, we have 2 errors, and therefore these efficient algorithms don't work. Now assume we guess a second time, and now we say we ignore position 2 and 3. Then we see that the error on the remaining positions has now Hamming weight equal to 1. And our code is also capable of correcting it, and therefore our algorithm works. Okay. Now let's summarize our algorithm quickly again. In other words, what the idea was that we want to ignore delta positions and decode in the remaining positions. Since we don't have any information, we just randomly guess, and if we guess enough erasures, our decoder works, and we do this over and over again until it's the case. Now let's look at the rank metric. How does it work there? First, let's define the rank metric by looking at an extension map. This map x gamma maps a vector of length n over fqm to its matrix representation, which is a matrix over fq with m rows and n columns. And the connection between the vector and the matrix representation is given down here. So assume we have a, or let's not assume we have it, let's define it, namely a basis gamma 1 up to gamma m of fqm over fq. And if we perform the inner product of the jth column of the matrix representation with this basis, we get the jth element of the vector representation. And with this extension map, we can define the rank weight of vector x as the rank of its matrix representation, and the rank distance of two vectors x and y as the rank weight of its difference. Now, what is an important property in this metric is the following one. Namely, assume you have a vector of rank weight equal to w. Then you can decompose its matrix representation in a matrix A, which has m rows, w columns over the base field, times a matrix B, which has w rows, n columns over the base field fq, and both are of full rank. Why this is important will become clear later, and I will also repeat it there again. Let's look at Gabidulin codes, which I mentioned on the introduction slide. You can now see that they are quite similar to Reed-Solomon codes, but are actually good in the rank metric. So Gabidulin code, which we denote here, is generated by a generator matrix. In the generator matrix, we put this vector G here in each row and power it from q to the power of 0 up to q to the power of k minus 1. So this is defined here. So this is rather similar to the Reed-Solomon code. What is a bit different is that now these elements G1 up to Gn don't have to be or they have to be distinct, but this is not enough. They also need to be linearly independent over fq. And if this is the case, then these Gabidulin codes have a minimum rank distance of n minus k plus 1. And as for Reed-Solomon codes, we know efficient algorithms, which are now able to decode any error up to rank weight n minus k half. For Reed-Solomon codes, it was Hamming weight up to n minus k half. With these two definitions, we can now formally state the problem that we are looking at in our paper. We call it the search Gabidulin code problem. And as instance, we have a Gabidulin code, which is specified by its generating vector G, an integer w, which is larger than n minus k half and smaller than n minus k. And we are given a vector r, which is a code word of a Gabidulin code, plus an error. And now the interesting thing is that the weight of this error is equal to w, and w is larger than n minus k half, which means, again, that we cannot use these efficient algorithms that I just mentioned. Similar to before, the objective is now to find a code word C prime of the Gabidulin code, which is in rank distance at most w from this vector r. And here I put again C hat, because the C hat does not necessarily have to be the same as C, but any C or C hat which satisfies this condition is fine. Okay, as before, we use error erasure decoder to solve this problem. But the question is now, what are erasures in rank metric? In Hamming metric, it was basically positions which we declared to be errors. Now, what is it in rank metric? For that, we call the property that I mentioned before, namely that the rank weight of this vector E, if the rank weight of this error is equal to W, then we can decompose the matrix representation of the error as A times B. Now we say that the row space of this error is equal to the row space of this matrix B. Okay, just that you know, in the following I will often say the row space of the error, and what I actually mean is we decompose it and then we look at the row space of this matrix B. Now assume you're given a subspace B hat of FQN, and we say that the dimension of this subspace is equal to delta, and the dimension of the intersection of this subspace with the row space of the error is equal to epsilon. Then we have the following success condition. Namely, we know that there exists efficient algorithms for the Gabidulin code, which are always able to solve the problem if the following condition holds. Namely, if this epsilon, so the dimension of the intersection of this given subspace B hat, and the row space of the error is larger than this quantity. And if you remember the slides that I showed you before for the Hamming metric and Reed-Solomon codes, this condition is very, very much the same. now just in the rank metric. What is the problem? The problem, as before, is that we don't have any information about the error. So what we do is, instead of guessing erroneous positions like in the Hamming metric, we are now guessing subspaces B-HUD. And then we feed these subspaces into the Gabidulin error erasure decoder that I just mentioned. And it turns out that these error erasure decoders succeed if the epsilon, so the intersection of this B-HUD with the row space of the error, is larger than this quantity, then, as I said, these algorithms succeed. Now, as you probably guess, the probability that this condition is fulfilled is rather small. And actually, it also determines mainly the work factor of our algorithm, which we show here. What you can see here is a term n squared, which comes from the fact that running the error erasure decoder one time has a complexity of n squared. Down here, we have the probability that the intersection of our guess is large enough with the true row space of the error. And we have here a term calligraphic n. And this calligraphic n refers to the fact that we don't need to find exactly the C which yielded that R, but any C which is in rank distance most W from R is sufficient. Now we can estimate all these numbers and lower bound it and then obtain this expression here. You can see it doesn't look very nice, and therefore I will also not read it out. And additionally, I think you cannot really get a feeling what this means. So what I would like to show you in the following are numerical results and also comparison to other algorithms that could solve the problem. You can see here different parameter sets. If you look at the first row, you can see that the parameters are rather small. And actually, these parameters were not suggested in any code-based crypto system. However, we choose them because they are small enough to make simulations. And what we did is that we run Monte Carlo simulations. So we really run these error erasure decoder on instances of the problem and estimated the work factor. And then we compared it with our analytical estimation. And what you can see is that our analytical estimation is very precise. So I think this is quite a nice result that it can be estimated so precisely. Then in the other rows, you can see parameters which were proposed in crypto systems. And what we did is that we compared our estimation with a generic decoder based on combinatorics, an algebraic generic decoder, and a different approach, which I call here W-key. Here, what we do is that we simply apply a key equation-based decoder on the problem instance. Then in the decoder, at a certain point, we are ending up with an underdetermined system of equation. And we have to go through the solution space to find a valid solution. And since the solution space is pretty large, we get pretty large work factors. What you can see is that our new proposed algorithm is for most of the parameters considerably better than the true generic decoders. But I would say this is also not too surprising, because here we actually use the structure of the Gabidulin code, and the generic decoders, as the name already says, are suitable for all kind of linear codes and don't make use of the particular structure of the code. This is different for the key equation-based decoder. Here we also make use of the structure of the code, but we can see that for a lot of parameter sets, our new algorithm is much better compared. However, what was surprising for us is that there are also parameter sets like this one here, where you can see that the work factors are actually pretty close. Okay, let me give some concluding remarks. What were further results? What we obtained in our paper. The first one is the following. So delta, so the dimension of the subspace that we guess, can be seen as an optimization parameter. So depending on the parameter sets, you should choose it differently to have the smallest work factor of our algorithm. And what we showed is that the work factor is concave in this parameter delta, which means you should choose it either as small as possible or as large as possible. What we further did is that we investigated if it's maybe possible to also use this error erasure decoder in a different way. Namely, there are error erasure decoders which are able to use parts of the column space of the error or a combination of column and row space. But what we did is that we showed that this does not improve our algorithm. So guessing the row space is optimal. Now, what could be future work? The first one is that there's a new algebraic generic decoding algorithm. I referenced it down here, and we did not compare our algorithm to it yet, but I think it would be quite interesting to see how they compare. Furthermore, I think it would be interesting to find new algorithms which try to solve this search Gabidulin problem that I just introduced. In the coding community, quite a lot of people try to solve this problem by polynomial time algorithms and were not successful. However, I think not too many people try to solve it in exponential time, and therefore I could imagine that there are also maybe other or maybe even better algorithms than our that solve this problem. Okay, that's from my side. Thank you very much for your attention and have fun at PQCrypto.